Hi everyone, welcome to the session. Today we are going to see what are image and kernel. Suppose we have two vector spaces V and W like this. Okay. Then we defined a mapping from mapping phi from V to W. Then the vectors in V can be mapped to W, and that mapped set is called image of phi. So this part is called this subset of W, which is being mapped from V, is called the image of phi. Okay, so image of phi is the set of vectors in W that can be mapped from vector space V. And we can say that this is actually a subspace of W. Okay, subspace of W. Image phi is actually a subspace of W. Okay, so when we take vectors from V and when we try to map it to the vector space W, we get a set of vectors here over here in the W space, vector space W. So those set of vectors are called the image of phi. And kernel, assume there is a neutral element in W, and okay, so that neutral element is represented like 0W. That is the neutral element in W, vector space W. And the set of vectors from V that have been mapped to the neutral element or the zero vector in W. So those set of vectors are called kernel of phi. Okay, so this is the kernel, and it of course includes the neutral element of V also. Okay, so this kernel of phi is the set of vectors in V. When we map these set of vectors into W, we will get the zero vector over here or the neutral element over here. So that is called the kernel, and again the kernel is a subspace of W. It is a vector subspace of V. Okay, and image was the subspace of W and kernel is the subspace of V itself. Okay. So kernel of phi is the set of vectors in V that maps to the neutral element in W, that is 0W. And coming to the definition, kernel, or in other words it is called as null space. It can be defined as follows: for phi, for mapping phi such that for mapping phi from V to W, kernel phi is equal to phi inverse of 0W. Okay, that means that when we do the inverse mapping of 0W to V, we'll get this kernel set. Okay, it is equal to the set of vectors V belongs to V such that phi of V will be 0W. Okay, so when we map these vectors, when we map these vectors, we will get the neutral element on W. So that is the definition for kernel or null space. And image is defined as image phi is equal to phi of V such that the set of all W belongs to the vector space W, such that there exists a V for belongs to V, vector space V, such that phi of V is equal to W. So when we map the vectors in V to W, we get the images. Okay, then these are the properties of this vectors. That is phi of 0V will be equal to 0W. That means when we map the neutral element from vector space V, we will get the neutral element in the vector space W. Okay, then a image of phi is a subset of W that we have seen in the previous picture. Like the phi of V is the subspace of W. Okay, then kernel of phi is actually a subset of V, and at the same time it remains as a subspace. Okay. So image is a subspace of W and kernel is the subspace of V. And phi is injective if and only if kernel of phi is equal to 0 only, 0 vector. Okay. Then there is a theorem relating this rank and nullity or the null space. Okay. So for vector spaces V and W and a linear mapping phi from V to W, it holds that dimension of kernel of phi plus dimension of image of phi is equal to dimension of V. So this dimension of kernel of phi, dimension means the number of basis vectors in kernel of phi plus the number of basis vectors in the image equal to the dimension of V. So we can pictorially represent it like this. Okay. Suppose we have these two vector spaces like this. Okay, one vector space over here V and the other vector space W here. Okay, take the basis vectors of V. Suppose we have n basis vectors over here, so like V1, V1, V2, etc. Vn, n basis vectors. Okay, these are n basis vectors of V. And out of these, some k vectors, okay, out of these, some k vectors will be mapped to the 0W. Okay, so k vectors will be mapping to the 0W. So dimension of this will be k. Then here the rest of the elements will be mapping to the other elements in the image of phi. Okay, so that is remaining n minus k elements are there. Okay, so this dimension of image of phi will be n minus k. Okay, so that means when we add these two, we will get the dimension of V itself. Okay, so that is the rank and nullity theorem. That is the nullity of V. That means which are the bases, how many number of bases have been mapped to the neutral element of W, plus the number of bases basis vectors that can be mapped to other vectors other than the neutral element in W. So that is n minus k, or we call it as the rank of V. Okay, so when we add these two, we will definitely get the dimension of V itself. So it is also called as the fundamental theorem of linear mapping. Okay, so that is rank and nullity theorem. Then the consequences of the theorem, if the dimension of image of phi is less than dimension of V, okay, then kernel of phi is non-trivial, that is the kernel contains more than 0V. Okay, and the dimension of kernel of phi is greater than or equal to 1. Okay, that means that in the kernel we have more than one element. Okay, the bare minimum element in kernel is always 0V. Okay, and if this condition satisfies, if the dimension of image is less than dimension of V, that means we have some remaining vectors in V that can be mapped to 0 element or null element in neutral element in W. Okay, so of course kernel will be greater than or equal to 1. Then if dimension of image of phi is less than dimension of v, then the system of linear equations fi of x, fi into x is equal to 0 has infinitely many solutions. Okay. Then if dimension of v is equal to dimension of w, then phi is injective and phi is surjective and phi is bijective. So all the properties will be there if the dimension of both the vector spaces are equal. Okay, those are the consequences. So that's all about the image and kernel. Thank you.